Hey everyone, I'm Harry and today I'm here to talk to you about web performance, but a very specific subset of web performance. I'd like to talk to you about largest contentful paint. Largest contentful paint, or LCP, is a relatively new performance metric, and over the next sort of 30 minutes we're going to learn all about how to optimize for it. My day-to-day work is as a consultant site speed engineer, I guess. And with that, I tend to work with fairly large clients. It's because large clients generally tend to feel the benefit of site speed more than smaller ones. But ever since Google announced their intent to take site speed into consideration when ranking you, I found that a much more diverse array of clients have started getting in touch, which is obviously very interesting for me. So now that site speed is part of SEO and part of rankings, a lot more people are aware of the importance. However, this isn't going to be an SEO talk. This is a performance talk, so we're going to get technical. So what is LCP? Largest contentful paint is a relatively new performance metric coined by Google in order to quantify how fast a page feels visually. When was the largest piece of content rendered? And it is one of 3 new metrics which form their core Web Vitals initiative. Quite a dry and, fairly technical definition is on screen right now. But realistically, what we're looking at is when was the largest piece of content painted to screen? And this is a much better proxy than legacy metrics such as load times. And of course, largest doesn't necessarily mean the most important, but it's a good kind of, well, like I say, a proxy for is the important stuff on screen quickly. For the Web Unleashed sites, Google would consider the largest piece of content this image element, and it is an image tag. On my site, for example, this is an image by appearance, but it's actually a background image in CSS. Interestingly, the meta.com website, the largest piece of content visually is that image in the background, except it's not actually an image, that is a video. And there are certain elements that are not considered for your largest contentful paint candidate. We'll look at that in a second, but it's very important to know which one is which. Video is not considered for largest contentful paint, and therefore it becomes this H1, so it's a text-based element. As I mentioned, it is one of 3 new metrics. We've got LCP, largest contentful paint. Also, we've got first input delay and cumulative layout shift. The reason I wanted to give this talk is because, surprisingly, the most origins struggle with LCP, and I think LCP is probably the simplest one to debug and fix. So what I want to do is kind of look at the pitfalls and maybe why people make so many problems and help them kind of fix them and get back in the green. So on screen right now it says a good LCP, but what is good? Well, as well as defining the metric, Google defined the thresholds, and they claim that an LCP, the largest contentful paint, in 2.5 seconds or faster would be considered good. This is pretty ambitious. What they're basically saying is you need to get the largest piece of content on screen within 2.5 seconds to qualify for giving a good user experience. That 2.5 seconds wasn't just plucked out of thin air. One of the sort of caveats they have when they define these metrics is to confirm a threshold is achievable, we require that at least 10% of websites on the internet currently meet the good threshold. What they're basically saying is 10% of websites can manage this, we think you can as well. That makes it kind of ambitious, but it also means the figure could change. If in 3 years' time, 15% of websites or 25% of websites manage this 2.5 second figure, they might make it a little more ambitious and a little smaller still. I mentioned this isn't an SEO talk, so what I want to briefly mention is if you're aware of Core Web Vitals, it may well be because of the new SEO impact. SEO is important. Search engine optimization is important for businesses, but the key thing to remember, SEO gets customers onto your site, but it's their experience once they're there that could be the make or break between them making a purchase or not. For example, a client I worked with only a couple of months ago, we managed to work out that a simple 500 millisecond improvement in LCP is worth 11.5 million euro a year. This is very big business and it really deserves taking seriously. So how do we get to good? Well, the whole point of this talk is trying to get you to that 2.5 seconds. The very first bit of advice I've got is solve everything beforehand. LCP is what is known as a milestone timing. A milestone timing is just a point in time that is usually preceded by n other things. And everything I've got on screen right now is one of those potential things. We could have DNS, we could have redirects, we definitely have time to first byte, which is kind of annoying because it's a bit of a miscellaneous metric. Loads of stuff here is that vital to getting this fast LCP. So what I would recommend is solving these things first, and your LCP should come faster kind of by virtue of solving things beforehand. The asterisks on the screen are simply to remind me to tell you that while these are web vitals, these aren't core web vitals. So the two, time to first byte and first contentful paint, Google actually consider these web vitals. Those are subtly but kind of importantly different to the core web vitals that we're dealing with today. A good example of this is a client I'm about to start working with. Basically, we can see on screen here, they lose 2 seconds to their time to first byte. Immediately 2 seconds are gone to time to first byte. If you've only got a 2.5 second budget for LCP, you can't afford to be losing 2 of it there. Then what we'll see is that everything from then on in just gets slower and slower until they're at 4.4 seconds. They've completely overshot their budget. Second bit of advice is choose the correct element. I mentioned this at the beginning of the talk. There are different elements that are considered for LCP, and they're not all born equal. This slide here is copied and pasted directly from the web.dev website, and this slide here is actually quite annoying to me because while Google have listed several different types of element that are possible to be LCP candidates, what they completely neglect to mention is that these have inherently different behaviors. Some of these are inherently faster than others. They don't list them in any particular order, so I've just copied and pasted it word for word. We've got image elements. We've got image elements inside SVG, and they are different, hence the different spelling. Video elements, they're poster images used. So the image itself comes from the poster attribute and not the first frame of the video. The video itself is kind of ignored. Elements with background images, and finally block level elements containing text nodes. So this could be a div or an H1 or a paragraph. Let's get the easiest one out of the way first. We love text-based LCPs. Hopefully, those of you watching will probably know enough about web development to realize that text is faster than images. A simple example of this is my own website. The exact same page, the exact same connection speed, the exact same image. This isn't even a responsive image. But just by having on mobile my LCP be text, we're coming in at 844 milliseconds. Switching the exact same page, exact same connection speed, exact same image to a large display, all of a sudden the biggest bit of content currently in the viewport becomes that image, which slips back to 1.4 seconds. We've lost 560 milliseconds there just by having a different LCP candidate. Also, I need to add, text is only fast if you're using the appropriate fallbacks. So make sure you're using make sure you're using font display in your font face declarations. But that's easier said than done. You can't just go and redesign your entire website to only use text and not images. So what about if your LCP candidate is a form of image? Well, remember, there are 4 possible image types. We've got the image tag itself, the regular image element, image in SVG, the poster image from your video, or a background image in CSS. So what we've got on screen right now is a very, very simple demo that I created. And the demo is basically one of each of the LCP types. But if I just made a page with just an image in it, that's always going to be pretty fast. So what I did is I put a blocking script in the head just to see how the browser would handle things. What happens when there's a critical asset in the head and we've got an LCP candidate in the body? Does the browser do anything interesting? Does the browser do anything clever? Does the browser do anything stupid? The results were quite interesting. I designed this test on purpose. I had a hypothesis. I had some suspicions. And in some ways, those suspicions were proved correct. In other ways, I was left quite surprised. If we plot the data, we'll see that image comes in at 1.4 seconds. Image in SVG is the fastest at 2.6. Poster, again, is 3.1 seconds, virtually identical to image tags. And finally, background image, by far the slowest at 4.3. So why these inherent differences? I found this very, very interesting. Why would Google list these 4 different available image types, but not mention the fact that they are inherently different speeds? When I plotted this data visually, when I plotted it as like a film strip, I noticed something very interesting. Any image here, or any screenshot with a red border, marks the largest Contentful paint moment. However, something's wrong. That frame is red, but there's no image present. Turns out there's a bug, and Chrome currently misreports image in SVG. When we adjust the data to take into account the actual largest Contentful paint time, we see that image in SVG is now pretty slow, 3.9 seconds. What this means, technically, if you want to game the system for a few more weeks, go and swap to image in SVG and something else will get counted as your LCP instead. But there's going to be a fairly finite limit on how long you get away with that. I want to visualize this data another way. I want to show you some waterfalls because this is where things get really, really interesting. We start to spot some patterns here. If we look at image and poster, the purple entry is images. That is our LCP image. What I want you to notice here is the fact that this is the first thing to get requested. This gets requested before the JavaScript, despite the fact it was defined second in the HTML. And then also it gets requested in parallel to the JavaScript. So we've got early discovery and parallelization. This is inherently pretty fast. However, if we look at the other two, image in SVG and background image, we get the complete opposite. The image is discovered second, which kind of makes sense, it was defined second, but it isn't downloaded in parallel at all. We lose parallelization completely, and the image isn't even requested until the moment the JavaScript is finished. This is the reason I designed that text. I was wondering if this happened. However, I was very surprised to see it happen with image in SVG, and we'll come back to that in a second. Let's step through our options. Image is good. We love image-based LCPs, and statistically, I think it's almost 50% of LCPs on the web currently are image tags. Image is pretty fast. Brief refresher. Image tags, sort of syntax, very simple. A source attribute and a mandatory alt attribute. And again, the waterfall looks like this. Complete parallelization, the image requested first. Now this is a very, very innocuous, very simple waterfall, but it allows me to teach you or tell you about something very, very significant. I want to talk to you about the preload scanner. The preload scanner is one of the most beautiful, elegant bits of browser internals you may have never heard of. The reason the image was discovered first, despite being defined second, is because of this thing called the preload scanner. Remarkably, IE8 invented it, but because it was Microsoft and enterprisey, they called it the speculative preparser. And what this does, what the preparser or the preload scanner does, is it decouples downloads and DOM construction. What that means is you get asynchronous downloads that can happen completely in parallel. Because previously, in IE7 and before, the same parser was responsible for parsing the HTML, discovering a file, downloading the file, running the file, then continuing to parse the HTML, discovering the next file, downloading, running, and all that had to happen in sequence. This was completely serialized. IE8 invented the preload scanner, which divorced the downloading from the execution of the page, which meant that they could be done asynchronously and in parallel. And the main point I'm trying to tell you here is that some resources are visible to the preload scanner, some are not. Resources that are not visible to the preload scanner will always be slower. And the good news is, image is visible to the preload scanner. It's easier to visualize than it is to just read text, so let's look at this. The top waterfall shows a browser without a preload scanner. Everything's downloaded sequentially because the browser has to read the HTML, download the file, read the next bit of HTML, find the next file, download, and so on and so forth. As soon as we invent a preload scanner, we get the bottom waterfall where all of these four things are done in parallel. This is way, way faster, and the great news is, as developers, we don't need to do anything to take advantage of this. It's right there inside every modern browser. However, what we need to avoid doing is hiding things from the preload scanner. Which brings me on to the next thing. Image in SVG is bad. The syntax for image in SVG is XML, so we need self-closing tags, we need our quotation marks. And you'll notice it is IMAGE, not IMG, so it's a significantly different, or it's a sort of completely distinct element from image HTML tags. The waterfall for this, complete serialization. Look at that, we've got no parallelization whatsoever. This is because images in SVGs, for some reason, are hidden from the preload scanner. It's going to take a long time for the browser to actually discover your LCP candidate if it's an image in SVG. So, currently reporting is broken, there's a bug anyway. Chrome misreports image in SVG, so you're going to get actually optimistic results. The bad news is, image, it turns out, is hidden from the preload scanner. It's inherently slow. Now, it's very unlikely you're using this in production. I've never seen this myself in production for real, but still I wouldn't recommend using it. It's going to be slow by default. A happy surprise was that poster was good. This really, really impressed me. The syntax for poster is just an attribute on the video element. And remember, Chrome will not take the video itself, it will take the poster image if it's provided. The waterfall is basically identical to the image tag, so we have the exact same behavior. This is really, really, this is very pleasant. I liked to see this. Poster behaves much like image, and it is available to the preload scanner. The important thing I want to tell you now, though, is that if you do have a video for your LTP, make sure you are using a poster image. If you remember the meta example I showed you earlier, Chrome took the H1, right? It didn't take the video because currently video itself isn't counted, the poster image is. That means that if you've got a video currently on your site and you're not using the poster image, your LTP is probably an H1. However, there is kind of whisperings, murmurings that Chrome may begin to use the first frame of a video for your LTP. And if they do this, you are really going to struggle to hit the 2.5 second threshold. Videos weigh a lot more than images. Images weigh a lot more than text. If you are using a video on your site, your LTP is probably going to be an H1 or something similar. If they release this sort of change and they decide to take the first frame of the video, it's going to be really important to get an LTP poster image in there instead, so you're not being held to the kind of very, very tight threshold of frames of video. The next thing is, or the last thing I suppose, is background image is bad. Background image is bad for performance. I knew this would be bad for performance just because I know how CSS works. This whole background image sort of scenario is exactly why I ran this test in the first place. I wanted to prove to people that background images are bad. It's in doing that I inadvertently discovered that image in SVG is bad as well. Background image will always be slow. The test I did here was I just put an inline style. I just put an inline style on the div. I didn't use an external style sheet because obviously that would naturally be slower because I'm adding more resources. So I just used an inline style. And what we'll see here is that even though this style tag is inside the HTML file, the image wasn't discovered until after the JavaScript had finished. This is because of how CSS and background images work. Background images, and indeed fonts, are what we call late discovered resources. Browsers only request background images when they find out the page actually needs it. Otherwise it'd be really wasteful. So the browser waits till it encounters a page and sees that, okay, this page or this DOM node needs a background image. The problem is, waiting until it discovers the DOM node is way too late in the process. The browser doesn't discover the DOM node until it's ready to display it to you. And by that point, it's too late. The image should be there already. So basically, background images and also web fonts, but they aren't part of your LTP, they're inherently slow. So I would really try and avoid using background image as your LTP. The important thing really here, I guess the takeaway is, CSS doesn't download images. The render tree does. And the render tree is the combination of your CSS object model and your docking object model transposed on top of each other. Once that is built, the browser knows what it needs to request. But that means that the browser only requests it when it finds the DOM node that needs it. That's way too late. So yeah, my advice here is try and avoid background images where possible, but I mentioned that my site uses a background image. So what I'll show you how to do later in the talk is how to sidestep that issue. So the takeaway here is not all candidates are born equal. Ideally, a text-based candidate with the correct font display would be the very, very fastest. Poster is nice and fast, but not likely to be used. Avoid image in SVG. If you can, avoid background images, but don't worry too much. Image is the most likely statistically, and it's also one of the fastest. So if you're using an image for your LTP, we're already onto a happy path. And a word of warning, if you are using video, just be careful. There may be an update to the sort of, not the algorithm, but the sort of the requirements that may end up penalizing you. The next thing I want to look at is some common mistakes. These are things that people frequently get wrong, which inadvertently harm their own LTP. Some of these are real facepalm moments. Some of these are a bit sad and upsetting, but we'll start with a facepalm. Don't lazy load your LTP. Just don't do it. Lazy loading makes images slower, right? There's a lot of naive performance advice. Load your JavaScript asynchronously. Well, that might make other things faster, but that will make your JavaScript slow. Loading your LTP lazily might make other things faster, but if you want to make your LTP fast, the last thing you want to do is lazy load it. Heartbreakingly enough, almost 10% of the web natively lazy load their LTP. A further 5 to 6% do it with JavaScript. So instead of using loading equals lazy, they're actually using JavaScript, which is even worse. We'll find out why in a moment, but just go and check immediately. Are you lazy loading your largest contentful paint element? If so, please stop. The native lazy loading is really simple. It's kind of probably why we're using it so much. It's just one attribute value pair, loading equals lazy. And one thing that developers ask me quite frequently is, can't we just add loading lazy to the browser, to the image, and the browser just works out what to do for us? This is really, really smart. Like, this is a clever line of thinking, but unfortunately, it's not good news. What developers are saying here is, well, the browser will only lazy load the image if it's out of the viewport, right? Or if we're on a slow connection. So if we just put loading lazy, the browser will decide that, oh, okay, I won't lazy load this one because this is in viewport. The problem here is that the browser doesn't know the image is in the viewport until it's about to paint the image, which again, similar to background images, is way too late. But even more interestingly, deliberately, by design, loading equals lazy hides the image from the preload scanner. Deliberately, by design, loading equals lazy turns the preload scanner off. What that means is if we go from a regular image at the top to loading equals lazy on the bottom waterfall looks just like image in SVG, looks just like background image, which are the two worst possible candidates. So don't lazy load your LCP. To try and check this, I often add this snippet to my client's style sheets. Any image with loading lazy, just put a 10 pixel solid red border around it, and what I'll do is I'll just click around the site looking for any images above the fold. These two images are problematic. I need to remove lazy loading from these images. The next tip is don't build your LCP with JavaScript. JavaScript is the fastest way to build a slow website. Put it down, leave it alone. A great example of this is iPlayer. And iPlayer is a wonderful organization here in the UK. It's a little bit like British Netflix. And I worked with them this summer to help speed up the iPlayer site. Like every kind of page and every kind of view of the application, we were trying to optimize. But an interesting thing came on the playback page, the actual page where you watch an episode. This page was 99% rendered on the server, so it was nice and fast, but for some reason, the actual video player itself and the image was built entirely on the client. It was completely client-side rendered. They put a big chunk of JavaScript in between the HTML and the image. What that means is at the top, the LCP was very, very slow. We had to request the HTML, then the 30th request was their main app bundle, then the 43rd request was their LCP image. What I did is I asked the developers just to refactor this, and it took them an hour or two, didn't take long at all, and they started server rendering that component as well. Obviously, most of the functionality, the interactivity comes from JavaScript on the client, but the actual static version of that page could have been 100% HTML. They eventually refactored to this, and we got that from being the 43rd request down to the 17th. There is still scope for optimization here. There's still more we could do. The primary thing we could do is self-host this image, but at least removing that JavaScript step saved us a bunch of time. In fact, we got this kind of improvement, and I think you can see exactly which day they deployed this change. It ended up being a 43% improvement for about an hour and a half, 2 hours work. Well worth doing for them. Okay, the next thing I just mentioned already is don't host offsite. And the best example of this is actually me. I made a mistake a couple of weeks ago. I accidentally moved my own LCP image onto Cloudinary. I love Cloudinary. I really, really do. Cloudinary do a great job of on-the-fly optimizing images. And of course, if your LCP is an image, you need it to be well optimized. That is such a basic fact that I didn't even include it in this talk. However, the cost of visiting Cloudinary is more expensive than having an unoptimized image, because look at this. A couple of weeks ago, I accidentally moved my LCP image onto Cloudinary, and you can see in the graph exactly when this happened. I went from a 2.1 second image time to 3.5 seconds, which completely takes me over the 2.5 second budget. Here I was failing the LCP Core Web Vital. What is interesting is the image was 1.5 times smaller in terms of bytes, but it took 2.6 times longer to download purely because of this trip to a different origin. So please, by all means, make sure you use things like Cloudinary or ImageX or Fastly's I/O. Make sure you're using that kind of stuff, but not for your LTP. Try and always self-host your largest Contentful paint candidate. Next thing is don't usurp your LTP, and this is a terrible word, usurp. It sounds so archaic. Basically, it means kind of to overthrow or undermine, or turns out another synonym for usurp would be dethrone. Don't dethrone your LTP. This one isn't a facepalm, this one's heartbreaking. The main candidate for this is going to be late-loaded modal overlays. Sign up to our newsletter, and that arrives sort of 5 seconds into the page load lifecycle, and it steals your LTP from your own image or your H1. Really interesting example of this was REI, a client I worked with earlier this year. And here on the left, the very far left of the screen, is the page sort of the day before, and the right-hand side of the screen is the page on the current day. What we'll notice is that LTP got 54% worse. Went from 8 seconds to 12.5, like a lot worse. Can anyone work out why? Well, what's interesting is, on day 1, their LCP was this H1, 46,000 square pixels. The cookie banner beneath it was 44,000 square pixels. So the H1 won. However, and it's a smart bit of sort of e-commerce platform that does this, they sold out of all their Cannondale bikes, so the CMS just redirected users to full suspension mountain bikes instead, of all brand types. So what happened there was the H1 got smaller, 33,000 square pixels, which left the cookie banner the largest element on the page at 44.5 thousand square pixels. This late-loaded cookie banner stole the LCP away from the H1. This is really heartbreaking when I see this because developers don't normally control the cookie banner. And normally when you're working on your development environment, you don't even see it at all. So my advice here is make sure you keep an eye on things in live and make sure you don't accidentally steal your LTP away from yourself. That would mean things like loading your cookie banner early and or making sure your cookie banner is not the biggest bit of content on the page. So that was a really heartbreaking one, and it was a simple one to fix. You just redesign this so that it is smaller than the actual most important bit of content. Okay, for the last part of the talk, I want to talk about stretch goals. I want to talk about things that more ambitious developers, and that's you lot, more ambitious developers want to go for this. Stretch goals is new things, new APIs we can use to make our LCP even faster. So we've solved all the previous problems. We're not making silly mistakes. We're now back to kind of ground zero, back to like a baseline. Next, we want to go further and really overachieve. The first thing is resource hints, and this is the one you're most likely to have seen before. These are the most widely deployed. If you've ever used pre-connect or pre-render or preload, you've used a resource hint before. The one we are most interested in is preload. Now, preload can and definitely is overused, so always, if you implement this stuff, make sure you test. The syntax is relatively simple. It's a declarative fetch for lcp.jpg, and these normally, though not always, go in the head. Use these sparingly. Make sure you don't use too many of these because, if you make everything important, you make nothing important. But preload just preempts the browser. It tells the browser, you don't know it yet, but you're going to need this file soon. So it's useful for late discovered resources. The clue is in the name here. Remember the preload scanner, right? Well, some things are hidden from the preload scanner. This resource hint is a great way to reintroduce them. It exposes things like background images to the preload scanner so they can be requested from the HTML, not from the CSS or the render tree. Generally speaking, I wouldn't advise using preload for resources that are already in the HTML. I would use it if your LCP candidate is a background image. On my site, I mentioned that I use a background image for my LCP, and that's kind of a bit of an anti-pattern, but preload helps me solve that problem. If you look here, on request 4, on the top waterfall, the JPEG here, the masthead image, my LCP image, is discovered after the CSS. It's discovered fourth, and it takes 932 milliseconds to download. The reason it takes 932 milliseconds is because the bandwidth is shared with the other resources downloading in parallel. There's only a finite amount of bandwidth available, and the browser is giving some of it to some HTML, some of it to some JavaScript, some of it to some other images. However, by using preload, what we'll see now is the CSS gets requested as the third entry, not the fourth. It gets requested in parallel to the CSS, so it's requested much earlier, but it only takes 445 milliseconds. It's more than twice as fast. And that's because the browser isn't giving any of its bandwidth to any other files. You can see this by the dark purple chunks. Dark purple is time actually spent sending data. Light purple is the browser kind of just hanging around. The server's not really doing anything, it's not sending anything. The purple in the second waterfall is really packed up tightly. That means the browser is receiving data continuously for this image. Way, way faster. Improved LTP by approximately 1.2 seconds. However, don't go and implement this without reading up on it first. Preload can be problematic. That link there is a very important talk about preload and some of the pitfalls. So please make sure that if you implement this, you read about the downsides and make sure you test everything. The next thing is priority hints, and I'm in love with priority hints at the moment. Priority hints are, again, a very simple syntax. It's fetch priority equals high, auto, or low. These usually go in the body, whereas preload usually goes in the head, though not always. But again, use these sparingly. Fetch priority is useful for in-page resources, or fetch priority high specifically is useful for in-page resources if you've got an image LTP. It reduces the amount of time spent queuing. It's incredible. It allows us to control priorities. But in order to understand that, we need to know what priorities actually are. This matrix shows a series of file types and their associated priorities. All files have an inherent priority that is defined by the browser. When the browser loads an HTML page, it effectively makes a kind of a shopping list. And what it wants to do is it makes sure it shops for the most important things first. So it'll get all of the sub-resources in a page and try and order them from highest to lowest priority. This means that the browser will request the most important things first and the least important things last, and it will give the correct resources to each file type. We only have a limited influence over these priorities. We can't do much to interject. That is until we were given the fetch priority attribute. This allows us to manipulate priorities ourselves. If you've done much performance testing before, you may have seen something like this. Initial priority set to low and requested priority is set to high. The browser can and indeed does change its mind about priorities as it learns more about that file. So what happens with most images is they're all requested as low priority, but if the browser notices the image is in the viewport, it will try and give it high priority to try and bump it up that queue. But again, by the time it knows this, it's already way too late. I'm going to show you a screen recording on the next slide, and I want you to keep an eye in the middle of the red circle. Here we go. See, that's set to low priority. Then all of a sudden changes to high priority. That file spent 2.16 seconds queuing. It spent a load of time at low priority, then the browser worked something out and changed it to high priority. I want to pull this sort of screenshot out into a static image just to look at the data a bit more clearly. What fetch priority does is it reduces the amount of time we spend queuing. It won't reduce the amount of time the browser takes to discover the resource because it needs to discover it when it gets to that line of the HTML. But once it does discover it, it tells the browser whether it should wait to request it or whether it should request it immediately. Without fetch priority, the browser doesn't know where that image is going to be just yet, and it spends 2.6 seconds working out that, oh my goodness, this is in viewport. This should have been high priority the whole time. So the browser found this image around 794 milliseconds, but spent 2.16 seconds queuing it. That's way too long. This gave us a 13.8 second LCP, which is terrifying, really. That's really not great. But that's because the browser didn't know the importance of this image until way too late in the process. What we did is we just added fetch priority equals high to that image tag. That's all we did. It's as simple as that. Now I'm going to show you the same screen recording again, but watch what happens in the middle of that red circle. Immediately high. Didn't spend any time at low priority. That gets me so excited. Again, I'm going to pull this out into a static screenshot, but look here. This spent 0.85 milliseconds queuing, right? It used to be 2.16, now it's 0.85 milliseconds. Put another way, that is over 2,000 times faster. That, for me, that is just staggering. For the sake of one HTML attribute, those are impossibly good gains. This gave us an LTP of 5 seconds, so still not great, but way better than 13, all for the sake of one attribute. This static slide is kind of a bit of a It's a bit of noise really, but the key highlights are we saved almost 100% of our time on queuing. So we went from 2.16 seconds to 2.159 seconds. We got a nearly 9-second improvement in LCP. Staggering gains for one attribute. The last thing I want to talk about is image decoding, and this is something I'm really excited about. This is by far the newest thing that I'm showing you. It's not very well documented, and therefore it's not very widely used. I'm going to start recommending people using this a lot more after I show you the tests that I ran. Now, image decoding is not very well defined, the spec obviously, but people don't tend to discuss it much, and when they do, they tend to say things like this. Image decoding is said to be synchronous if it prevents presentation of other content. It doesn't tell you if it's good, if it's bad, it doesn't tell you when you should use it, doesn't tell you what the use cases are, doesn't tell you when to avoid it. Everything's pretty vague around image decoding. But basically, I'm here to help you demystify it and work out when to use it. Image decoding tells the browser how to deal with image decode tasks. Decoding sync is useful for your LCP candidate. We also have async and auto. I wouldn't recommend using auto because you don't need to. Async, we may have some use cases for that, but we are going to focus on decoding equals sync, which I guess is confusing given that this slide says async. So actually, I've got ahead of myself. What we're looking at here is what would happen if we told the browser to asynchronously decode our LCP? Well, what we would end up with is something like this. So I ran a performance profile on this very, very beautiful screen right now. This beautiful looking screenshot shows us a few things. Around here, you can just about see we got one thin sliver of the image beginning to get decoded. The next frame, this is like a new visual frame, actually shows nothing new above the fold. It's still the same amount of decoded image. So we've got a new frame shipped to the browser, but we don't see any change. It's not until this third and final frame that we actually see the full image decode. Now the reason for this is this image was decoded asynchronously. We allowed the browser to do other things in between. So the browser decided to do some recalc style and layout tasks below the fold. This was the browser painting and working out the layout of paragraphs off screen. This is what happens if you asynchronously decode an image. This led to an overall time of 700 milliseconds, which is a bit too long. If you've got 2.5 seconds of budget for your LCP, losing 700 milliseconds of that just to decoding the image means that you're on the back foot. It's really going to be hard to achieve. So let's see what happens if we force a synchronous decode. Well, it's a much prettier picture, which was not actually an intentional pun, but I'm going to leave that in. First frame, we see that thin sliver of image again. Second frame, image fully decoded. There isn't a third step. We don't do anything else because we told the browser to synchronously decode this image. Don't do anything else. What that means is the only tasks in the interim are image decode tasks. That leads to an overall time of 324 milliseconds, way over twice as fast. Now the thing is here, the browser didn't decode the image any faster. It still took n amount of time to decode the image. The key thing is the browser didn't do anything else in between. It only did image decode tasks. This is so much faster, and therefore what I'm going to recommend to most of my clients is for your LCP image, if it's an image tag, add fetch priority high and add decoding equals sync. Therefore, the flip side is any below the fold images, perhaps try adding loading equals lazy and decoding async. Notice here that we don't need fetch priority equals low because loading equals lazy implies that anyway, so it'd be redundant to add fetch priority low here, but loading lazy and decoding async for below the fold images. I just looked at my timer down there. I've gone over time. I'm really, really sorry. I'm going to try and summarize this entire talk, of which there are 105 slides, in one final slide. Let's put it all together. LCP is the final metric. Solve everything else beforehand. If you've got a bad time to first byte, solve that before you worry about LCP. Choose the best candidate. If you can, go with text. If not, try and go with image. Expose the LCP candidate nice and early. Don't hide it away in JavaScript. We love HTML. HTML is fast. Don't make silly mistakes. Try and work with the grain rather than against it, and help the browser when you're smarter. When you know better than the browser, lean on these new APIs. But finally, especially with new features, make sure you test absolutely everything because you can inadvertently go too far and accidentally make your site slower. So whatever you implement from this talk, please test it before you deploy it because I don't want that responsibility. Again, I have gone over by nearly 10 minutes now, so I'm very, very sorry, and thank you for your time. I guess I'm ready to take questions, so thank you very much for listening.